Okay, unit number 4, solution chemistry, acids and bases, and oxidation reduction reactions. This unit really breaks apart into those 3 major categories, starting with solution chemistry, which is where we're going to review the ideas of molarity, the solubility rules, predicting products, solubility curves, etc. So let's get started right away with number 28, and it is a problem involving molarity. How many grams of aluminum nitrate are needed to make 350 milliliters of a 1.45 molarity solution? So step 1 is we need to know the chemical formula for aluminum nitrate. So we start with the ions. Al plus 3 based on its location, nitrate NO3 negative 1, polyatomic ion. Now we need to crisscross those charges like we've been doing all fall, and we end up with Al NO3 parentheses 3. So now we have our chemical formula of aluminum nitrate, and our next step is to use the information provided to calculate the number of moles that's required, and then finally we'll convert that number of moles from moles to grams. So you need to be showing all your work, so the next step would be to show the formula you're going to use. Molarity equals moles over liters, and remember these formulas are in the reference booklet. And then substituting in, the molarity is given as 1.45, moles is what we're solving for, and the volume 350 milliliters converts to 0.350 liters. And then solving for moles, we would simply cross multiply, assuming that we are remembering that that's the same thing as over 1, and we end up with moles equals 0.5075. Now, in this case, we're thinking of moles as like a variable. So I recommend that you rewrite the word moles here, because then you're showing it as a unit. And then the next step would be to convert that from moles to grams, remembering that 1 mole of any substance is equal to the molar mass of that substance. And when you add up AlNO3 parentheses 3, it adds up to 213 grams according to the periodic table. Now, if your teacher has instructed you, just like I said in the stoichiometry unit, to go beyond the tens place for your molar masses, then you should do so. But this section also will be based on my rule in my class, which is to round to the tens place. And then once we apply significant figures, there's 3 sig figs in both of these original numbers, so our final answer should also have 3 sig figs, and it comes out to 108 grams AlNO3. And that's why you need to know the chemical formula, because the only way you can get the molar mass for this substance is by writing the chemical formula of AlNO3. Okay, so on to number 29. If 2 grams of sodium sulfate are dissolved in 20 milliliters of solution, what is the molarity of the solution? So this is where you can either convert from grams to moles first, or you can use the idea of combining a molar mass conversion with the molarity formula, which results in molarity equals mass over molar mass divided by liters. So, using that idea, my mass is 2 grams. Now I need my molar mass of sodium sulfate. So again, we're going to need a chemical formula for this. Sodium sulfate is Na2SO4. I think I've crisscrossed enough formulas that we now know we get the charges, cross them. And now we're going to add up to get the total mass of Na2SO4 according to the periodic table. That comes out to 142.1. So that's the top of our fraction, divided by liters. It's 20 milliliters of solution, so converted to liters will be 0.200, keeping our zeros for significant figures purposes. And when we divide, this one comes out to 0.684 molarity Na2SO4. 3 significant figures in our final answer, because there are 3 significant figures in 2 grams and 3 significant figures in the 20 milliliters, and the molar mass is not used for significant figures purposes. On to letter A, the molarity of sodium ions. So it means based on the previous problem. So this is one where you have to think about the dissociation equation. Now, whether you write the full dissociation equation or not is up to you, because the question only asks for the molarity. But I'm going to show the dissociation equation just to make sure that you understand where this is coming from. So this is saying that if the molarity of sodium sulfate is 0.684 molarity, again from the previous problem, then the molarity of the sodium ions will be a factor of 2. So you would have 0.684 times 2 for a total of 1.37 molarity Na plus 1 ions. It didn't, but if it did ask for the molarity of the sulfate ions, it would be 0.684 because coefficient of 1. On to the next page. We're now on page 10, continuing with the solutions half of this unit. And it says, for the next several questions, use the solubility curve on page 12 of your reference booklet. So you're going to have to refer to that, and I'm just going to show you and talk you through the concepts of what you would do for each one of these. It says, is a solution of 10 grams of potassium chlorate, 10 grams KClO3, in 50 grams of water, a saturated, unsaturated, or supersaturated solution. Well, when you look at your solubility curve, you'll find out that it's set up for 100 grams of water. So in order to determine how many grams would be in 100 grams, you set up your proportion. Now, again, this is a pretty easy one, and I'm sure we all can see that 50 to 100 is a factor of 2. So what's going to go up here is 20. But the reason why it's important to know the concept of using a proportion is so if it's not simple, like 50 to 100, you know you can solve it using a proportion. So what would a solution of 20 grams and 100 grams for KClO3 be? Saturated, unsaturated, or supersaturated? And it is, in fact, supersaturated. Why is it supersaturated? Because the point is above the line. On to number 31. What is the mass percent of a saturated solution of KNO3 at 50 degrees Celsius? So using the chart, you find the line for KNO3, you find 50 degrees Celsius, and you travel up to the line and over, and you'll find out that a saturated solution will contain 85 grams KNO3 in, again, the graph is based on 100 grams of water. So now to do the mass percent, we need the mass of the part, the KNO3, 85, over the mass total. The total is 85 plus 100, or 185. Times 100 to make it a percent, and this one comes out to 45.9% KNO3. Number 32, what is the molality of a saturated solution of potassium iodide at 15 degrees Celsius? Again, find your potassium iodide line, which is Ki, and go to 15 degrees Celsius, follow up to the line, travel over, and when you read the graph, a saturated solution of Ki will be 140 grams of Ki in 100 grams water. Again, 100 grams water because that's what this graph is based on, as you can see on the Y units. Now, what's molality? Molality is moles of solute over kilograms of solvent only. But again, this one can be modified, just like I did with molarity on the previous page. And mass divided by molar mass is the same thing as moles. And then on the bottom, I'm even going to tailor to the problem even more so by saying kilograms of water, because it tells us in the problem that water is the solvent, and most often is. So now we're ready to plug the numbers in the appropriate spots. The mass of the solute is 140 of the Ki. Molar mass of Ki, 1K, 1I, is 166.0. And then 100 grams of water is 0.1 kilograms. Calculator, and 8.43 molality Ki. Remember, molality is the cursive or italicized lowercase m. And that takes care of the questions that relate back to the solubility curve on page 12 of your reference book. Number 33. Before I get into number 33, just let me remind you with those solubility curves, in general, if a point is above the line for a substance, that indicates a supersaturated solution. If it's on the line for a substance, saturated, and if it's below the line, it would be considered unsaturated. Okay, so now continuing with number 33. Number 33 was the last major concept in the section regarding solution chemistry, and that was where we wrote complete balanced equations and then wrote full ionic equations and ionic equations identifying both precipitates and spectator ions. So in this particular question, number 33, A asks us to write the complete balanced symbolic equation for this reaction. And I'm going to pause for a second and write the reaction out, and then I'll talk you through it. Okay, as you can see here, I have the full balanced equation written for when solutions of sodium sulfate and iron 3 nitrate combine, and it tells you that a precipitate forms. So step 1 would be for you to use the charges in crisscross to get the two reactants, Na2SO4 and FeNO33, and then utilize your solubility rules to determine that sodium sulfate, it's a sap, is soluble, and iron 3 nitrate, which is a can, would also be soluble. Then you predict your two products. Sodium nitrate being one, both a sap and a can, so definitely soluble, labeled aqueous, and iron 3 sulfate, insoluble according to the sulfate rule. So now we're ready to identify the precipitate, and in this case the precipitate is the iron 3 sulfate. It doesn't specify what it wants, so you could write the precipitate according to the chemical formula, which is what I would be more likely to do, or you could write the actual name, chemical name of the precipitate, which is iron 3 sulfate. Next, identify the type of reaction. This is a double replacement reaction. It is two ionic compounds where the cation and the anions are switching. Next, identify the spectator ions. The spectator ions are going to be the ions that cancel out of the final net ionic equation, and the reason they will cancel out is because they are soluble on both the reactants and the product side of the reaction. And even without writing the full ionic and net ionic equation, I can identify who that's going to be, because if I look back up here, I can see that on the product side, sodium nitrate is going to be aqueous, and on the reactant side, the compounds that contain both the sodium and the nitrate are also aqueous. So my spectator ions are aqueous here, the sodium and the nitrate. And people often ask, do I need to include the coefficients? It's asking you who. It's saying identify them. So it's not interested in how many. It wants to know their identity or who. And then the last thing on this page says to write both the full ionic and the net ionic equations for this particular reaction. And once again, I'm going to pause for a moment and write this out, and then I'll talk you through it rather than the time consuming of you watching me write it. Okay, so here's my full ionic equation. So every time a substance is aqueous, so if you look back up here to the original, the sodium sulfate is aqueous, so that's why I'm writing it as separate ions. The same thing with the iron 3 nitrate. You can see the original designation is that it's aqueous. So down here on my reactant side of the equation, I have 6Na plus 1 plus 3SO4 negative 2 plus 2Fe plus 3 and 6NO3 negative 1. You have to write the total number of ions, so you must take both the coefficient and subscripts that indicate the number of ions into account. You include the charges, and you should technically include the aqueous symbols on each of these, but as you remember in class I said you could drop them out of the full ionic equation just to make it a little less cumbersome when you're writing it. Jumping over to the product side, sodium nitrate is aqueous, so we end up with 6 sodium ions and 6 nitrate ions, but the iron 3 sulfate is the solid substance or the precipitate. So we leave that together, written as a unit, because we're indicating that it doesn't break apart upon reaction. It'll stay together and precipitate out. We'll see it as a solid. We saw that in the lab. And now, last but not least, the final step would be to write the net ionic. This is where your spectator ions will cancel out. This is a nice double check, because if your coefficients and ions don't match up from left to right, you know you've had a problem somewhere along the line with indicating the total number of ions. And the final answer then is what remains after you cancel the spectators. This is where I require that you put the aqueous symbols back in for your ions on the reactant side, and I included the solid symbol all the way through. But again, everything should be labeled with regards to states of matter when you get to that final net ionic equation. Also notice that there are no charges in the compound on the product side because it's not acting as an ion. It's an ionic compound. The charges only are present on the reactant side where the substances species are in their ion form. And that takes care of page 10, and we're going to continue on with the top of page 11. When you go to the top of page 11, that final question is the last of what we covered in the solutions portion of Unit 4, and that's distinguishing between a strong, weak, and non-electrolyte. And so again, I'm going to hit pause and go ahead and define these and list an example of each. Okay, the different types of electrolytes. This has to do with whether a substance dissociates upon dissolving in water or not. And things will dissociate if they are ionic. And then the question becomes, do they dissociate nearly completely, or is there only partial or some dissociation? In the case of a strong electrolyte, you have nearly complete dissociation, and with an electrolyte tester, you will see a bright light of the light bulb, and sodium chloride is an excellent example of this. All strong acids and strong bases also fall in this category. A weak electrolyte is a substance that is in fact ionic but does not dissociate completely. In fact, it has partial or what's sometimes called some dissociation. With an electrolyte tester, you'll get a dim light. Vinegar is a good example of this. Also, weak acids and weak bases also fall in this category. And last but not least, a non-electrolyte. Non-electrolyte is chemically different. It is a molecular compound. So there is no dissociation of ions because there's no ions to dissociate. They are molecules. They remain as molecules when they dissolve in water. The electrolyte tester, you will see no light up, and a good example of this is sugar. Okay, number 35 goes back to a molarity calculation, but it's a different kind of molarity calculation. This is molarity with dilution. So in number 35, this is not a molarity equals moles over liters. This is an M1V1 equals M2V2. Let me try to help you understand why as we read through the question. If 350 milliliters of 0.45 molarity KNO3 is diluted to a total volume of 1,750 milliliters, what is the molarity of the resulting solution? So this is a solution of KNO3 which is then diluted with water to create a new concentration but still of the same solution. No reaction has taken place. That's what makes this an M1V1 equals M2V2. The starting molarity was 4.50 molarity and the starting volume 350 milliliters. It wants to know the resulting molarity, M2, and it tells you that it's diluted to a total volume of 1,750 milliliters. So it's telling you that's the new volume, or the V2. To solve for M2, you'll divide both sides of the equation by 1,750, cancels on this side, and M2 is 4.5 times 350 divided by 1,750. Applying significant figures, your final answer should have a total of 3.900 molarity KNO3. Number 36. Number 36 is Bronsted and Lowry equations and acid and base theory. In this particular question, it's asking you to complete the equation and identify the acid, base, conjugate acid, and conjugate base. So in this first one, you have to remember water is a substance that's amphoteric, which means it can serve the role as the acid or the base. So you must use the other substance to determine what the likelihood is of which role water is playing in this case. And HCN is in fact an acid. It starts its chemical formula with hydrogen. So there's our acid. H2O is the base. Just to be 100% complete, we can even go so far as to put our states of matter in there. Aqueous and water is always a liquid. And then acids donate a hydrogen ion and bases receive a hydrogen ion. So the HCN becomes CN -1, aqueous, reverse role, conjugate base, plus water receives as the base H3O plus 1 or hydronium ion, and this also aqueous, and this one reverse role will be the conjugate acid. In the next problem, water in this particular scenario is going to serve the role as the acid because NH3 is a weak base. Again, including our states of matter, we'd have aqueous and liquid, and the acid donates the hydrogen ion, the base receives. So NH3 receives a hydrogen and becomes NH4 plus 1 aqueous, reverse role, conjugate acid. The H2O has given the hydrogen ion in this case. What remains? A hydroxide ion, aqueous, reverse role, conjugate base. In the next section, it asks you to calculate the pH, POH, H+, and OH- in each of these scenarios. And what I'm going to do just for simplicity's sake is I'm going to take you through the dissociation for each one of these because that's typically the more difficult piece for students, and then I'll simply fill in a table for each of the different items. So what we're going to have here is we're going to have an H+ concentration, we're going to have an OH minus concentration, we're going to have a pH, and we're going to have a POH. And again, think of these as like column headings for all of the rest of this page, A, B, and C. So starting with 0.1 molarity HCl, you have to remember that you have to decide how this dissociates. HCl will dissociate into H plus 1 and Cl minus 1. This is what helps you to know that it starts out as HCl, and if you don't immediately recognize that as one of the strong acids, you should then, once you write it, say, oh wait, it makes a hydrogen ion, this has to be an acid. The relationship between HCl and H plus is 1 to 1, so the concentration of H plus is 0.10 molarity. So I can come right over here and complete that box, and then complete the other three according to the relationships in your reference book. Let's just keep going right on to the next one from the dissociation perspective. The next one is H2SO4. Again, a strong acid, so it will completely dissociate into 2 H plus 1 ions and 1 SO4 negative 2 ion. So in this case, the starting molarity is once again 0.10 molarity H2SO4, but because of this 2 in front of the H plus, when I determine my H plus concentration, it's 0.1 times 2, or 0.20 molarity. So in the second question, my hydrogen ion concentration, 0.2 molarity. And then in the last group, we now have a base, calcium hydroxide, and it's in fact a strong base. So when we take calcium hydroxide, CaOH2, and the reason it matters it's a strong base is complete dissociation, we'll end up with Ca plus 2 plus 2OH minus 1. So there's my base ion. If my starting concentration of calcium hydroxide was 0.1 molarity, because of this 2, my hydroxide ion concentration will be 0.20 molarity. So now when I jump over here, this is my hydroxide column, 0.20 molarity. So now I'm going to work through, and I'm just going to talk through how you would calculate the others and then fill in the answers. So if I have hydrogen ion, I can get hydroxide using the KW formula. 1 times 10 to the negative 14th equals H plus times OH minus. Once I have both the H plus and the OH minus concentrations, I can get the pH and the POH by doing negative log of the H plus will give me the pH, negative log of the OH will give me the POH. And then I can double check to make sure my answer makes sense because pH plus POH equals 14. What if I had a different scenario where my starting point was a pH or a POH? That's when you're doing the reverse process, which is inverse or second log negative pH gives you the H plus, and second log negative POH gives you the OH. So now how about the answers for all of these? And now you can see all of the boxes completed for the rest of this page. And we've got one page to go as we flip to the top of page 12. And when you go to the top of the page 12, that's where it's going to utilize what I just reviewed. What if you're given a pH and you're trying to go in the reverse and get the H plus? You have to remember that H plus is 10 to the negative pH. And so this one works out to 5.623 times 10 to the negative 11th molarity H plus 1. Moving along to number 39. Number 39 is a titration problem. So you're going to need number of hydrogens times molarity of acid times volume of acid equals number of hydroxide ions. Technically I should put my plus 1 in there and my minus 1. Times molarity of base times volume of base. And again, this formula is found in your reference booklet. You can write the full balanced equation for the neutralization reaction, or you can simply look at your formula for your acid and your formula for your base to get your number of hydrogens and your number of hydroxides. So in this particular case, the number of hydrogens is 1. The molarity of acid is what we're looking for. The volume of acid is 27 milliliters. On the base side, the number of hydroxides is 2, OH parentheses 2. The molarity of the base is given as 0.250, and the volume of the base is given as 35 milliliters. To solve for M sub A, or molarity of acid, we're going to divide both sides by 1 and 27 and end up with the molarity of our acid is 0.2 648 molarity HCl. And again, the numbers for number of hydroxides comes from right there, and number of hydrogens, there's a subscript of 1 on the HCl, comes from right there. And now we're to the final section of Unit 4. Remember I said it breaks into about 3 different sections: solutions, acids and bases, and now oxidation numbers. And number 40, 41, and 42 cover the concept of oxidation numbers. So let's go ahead with identify the oxidation numbers for each element in each of the following. And this follows the oxidation number rules. Using the method of showing the oxidation numbers across the top of the substance and the total charge calculation underneath to keep track and make sure we're essentially proving that our oxidation numbers make sense. Remember, when you have a compound that's made up of more than 2 elements, you want to do the elements that are on the outsides, the left and the right of the compound first, assuming that oxygen is not in the center. If oxygen is in the center, it's still always -2. So my oxygen is -2. According to location, my sodium is +1. Now to do my total charges, oxygen would be -2 as I multiply down, sodium +1. This is a compound, so the oxidation number total charges must sum to 0. So the chlorine in this case has to be a +1. +1, +1, -2. So my oxidation numbers in this case are sodium +1, chlorine +1, oxygen -2. Moving on to the next substance I have, which is actually a polyatomic ion. The difference in a polyatomic ion is the sum of the total charges will equal the overall charge on the polyatomic, which in this case is -2. That -2 is not the oxidation number on oxygen. That's just coincidental. Oxygen is always -2, so I'll go ahead and write that one in. -2 times a total of 4 oxygens is -8. It must sum to -2, so the carbon total charge must be +6. +6, -8 makes -2, divided by 2, +3. So the oxidation number on the carbon is +3, oxygen is -2. And last but not least, a positive polyatomic ion, ammonium NH4+1, means the total charges will sum to +1. In this case, hydrogen acting as +1. So when we do +1 times 4, we'll get a total of +4. And then what must the nitrogen be to sum to +4? It must be -3. 1 nitrogen ion, so the oxidation number on the nitrogen is in fact, sorry, I was making a positive by accident there, -3. So in the last one, nitrogen is -3, hydrogen is +1. Define the following: oxidation and reduction. This can come right from your notes. Oxidation is the loss of electrons, and reduction is the gain of electrons. And the final question asks you, for the following equation, can you identify the reactant which is oxidized and the reactant that is reduced? So it's looking for you to first assign oxidation numbers. Remember, if something is alone and not already given an oxidation number, its oxidation number is 0. That's the case here with copper. The silver is you're already indicating that it's an oxidation number of +1. On the right-hand side, the silver will be 0, and the copper is already assigned an oxidation number of +2. So the copper is going from a 0 oxidation number to a +2. That means that the oxidation number has increased, which is oxidation. And in the case of the silver is going from an oxidation number of +1 down to an oxidation number of 0. A reduction in oxidation number is, in fact, reduction. And that brings the entire review packet to a close. I hope you have found the videos helpful.